Inside a black hole, the direction toward the singularity has the same character as the direction toward the future. You cannot choose not to move toward it, just as you cannot choose not to move forward in time. Subscribe if you want more of the cosmos. This is white space. Settle in. There is an idea so extreme, so geometrically brutal, that when it first appeared in scientific writing, most people assumed it was a curiosity rather than a prediction. In 1796, the French mathematician Pierre-Simon Laplace performed a calculation of almost unsettling simplicity. He asked, if a body is massive enough and compact enough, could its escape velocity exceed the speed of light? His answer was yes. And the implication followed immediately. Any light produced at the surface of such a body would fall back down. Unable to leave, the object would emit nothing. It would be, to any observer, perfectly dark. Laplace was working with Newtonian mechanics, and for different reasons the idea was set aside. The wave theory of light, gaining ground at the time, suggested that waves might not be affected by gravity at all, a reasonable assumption in classical physics, but ultimately wrong. The idea went dormant for over a century, not because it was disproved, simply because the framework needed to take it seriously did not yet exist. That framework arrived in November 1915, when Albert Einstein completed the field equations of general relativity. The theory replaced Newton's concept of gravity as a force with something more fundamental. The statement that mass curves space-time and objects moving through curved space-time follow the straightest possible paths. What we perceive as gravitational attraction is the result of objects following those curved paths through a curved geometry. The apple does not fall because the Earth pulls it. It falls because the space-time around the Earth is curved and the straightest available path for the apple leads downward. Within months, in 1916, the German physicist Karl Schwarzschild derived an exact solution to Einstein's field equations while stationed on the Eastern Front during the First World War. He was computing the geometry of space-time around a perfectly spherical, non-rotating mass. What he found, buried in the mathematics, was a critical radius, a threshold below which the fabric of space-time curved so severely that nothing, not matter, not radiation, could escape. He sent the solution to Einstein from the battlefield. Einstein presented it to the Prussian Academy of Sciences. Schwarzschild died of illness on the front a few months later, not knowing what his radius would eventually be called. For decades, the Schwarzschild solution was regarded as a mathematical artifact, technically correct, but physically irrelevant, since real stars were messy and imperfectly spherical. Then, in 1939, Robert Oppenheimer and his student Hartland Snyder published a paper showing that a sufficiently massive star, upon exhausting its nuclear fuel, would undergo irreversible gravitational collapse. The mathematics did not terminate in some stable endpoint, it terminated at the Schwarzschild radius. In the same year, Oppenheimer began work on the Manhattan Project, and the black hole paper was largely forgotten. It would take another generation of physicists working in the 1960s, armed with better tools and a deeper appreciation of the field equations, to return to the problem and recognize what it actually implied. It was John Wheeler, the Princeton physicist who had initially resisted the idea of gravitational collapse, who in 1967 proposed the name that stuck. He needed something short enough to say in a sentence, vivid enough to carry the physics intuitively, and neutral enough not to prejudice the interpretation. He proposed black hole. The name immediately displaced the technical alternatives. And the concept it named began, from that point forward, to be taken seriously as a physical reality rather than a mathematical curiosity. The Schwarzschild solution describes a black hole that is perfectly spherical and non-rotating. Real astrophysical black holes formed from rotating stars are neither. The solution for a rotating black hole was found in 1963 by the New Zealand mathematician Roy Kerr, nearly half a century after Schwarzschild's work. the Kerr metric introduced a new level of complexity. A rotating black hole does not merely curve spacetime, it drags it. The rotation of the mass pulls the fabric of spacetime around with it, the way a spinning ball submerged in honey would drag the honey around its surface. This effect is called frame dragging or the lens stirring effect, and it has been measured directly. The gravity probe B satellite launched in 2004 detected the tiny frame dragging distortion produced by the rotation of the Earth with an accuracy of about 19%. Around a Kerr black hole, frame dragging creates a region outside the event horizon called the ergosphere. The boundary of the ergosphere is called the stationary limit surface. Inside the ergosphere, no physical object can remain stationary relative to the distant stars, no matter how much thrust it applies. Space-time itself is rotating faster than the speed of light would allow a stationary object to keep pace with. The object is carried along, but crucially, inside the ergosphere, an object is not yet inside the event horizon. It can still escape with sufficient energy. This asymmetry was recognized by the British physicist Roger Penrose in 1969, who described a mechanism now called the Penrose process. An object entering the ergosphere and then splitting into two fragments can, under specific conditions, cause one fragment to fall into the black hole, while the other escapes with more energy than the original object possessed. The extra energy comes from the rotational energy of the black hole itself. The black hole slows down fractionally. Over many such interactions, the rotational energy of a Kerr black hole can in principle be extracted and used. A maximally rotating black hole stores an amount of energy in rotation equal to about 29% of its total mass energy for a stellar mass black hole. This represents an enormous reservoir. Astrophysical jets from active galactic nuclei are thought to be powered, partly through this mechanism, extracting energy from rotating supermassive black holes at the cores of galaxies. Penrose received the Nobel Prize in Physics in 2020, shared with Andrea Ghez and Reinhard Genzel for the observational confirmation of Sagittarius A star, in recognition of his theoretical works showing that singularities are a generic prediction of general relativity rather than a special artifact of symmetric configurations. His proof, the Penrose singularity theorem, established that once a trapped surface forms, a singularity is inevitable regardless of the shape or rotation of the collapsing object. The optimism that irregularities would prevent collapse from reaching the Schwarzschild limit was shown to be unfounded. What physicists now call a black hole is not a hole in any conventional sense. It is a region of space-time where gravity has won completely. Every path through that region, every trajectory available to light, to matter, to information curves inward. The boundary of this region is called the event horizon. It is not a surface you could touch or see. It is a mathematical threshold, a point of no return, defined not by any material but by geometry itself. To understand what gravity does to geometry, consider the following. Imagine you are measuring a vast circular region of space, far from any massive object. You walk its circumference, you measure its diameter. The ratio of those two numbers will be pi, as Euclidean geometry requires. Now place an enormous mass at the center. The mass curves the space around it. Walk the same circumference, measure the same diameter. The ratio is no longer pi. Space is not flat. The mass has changed the shape of the geometry in which you are embedded. This is not an effect that gravity produces on space. According to general relativity, this warping is what gravity is. The consequences become visible at cosmic scales. When light from a distant galaxy passes near a massive foreground object, another galaxy, a cluster, a concentration of dark matter, the light does not travel in a straight line. It follows the curvature of space around the mass, bending toward the center. From our perspective, the image of the background galaxy is distorted. It may appear as an arc, as multiple copies, or in cases of near-perfect alignment, as a complete ring surrounding the lensing mass. Einstein predicted this effect in 1936. It was confirmed observationally in 1979, and since then, gravitational lensing has become one of the primary tools through which astronomers map the distribution of dark matter, matter that emits no light but whose gravitational influence on geometry leaves a measurable imprint on the paths of photons. The effect intensifies as you approach the mass. Near a neutron star, the deviation from flat space is already dramatic. Near the event horizon of a stellar mass black hole, a remnant left behind when a star heavier than roughly 20 times the mass of our Sun collapses, the curvature becomes extreme beyond ordinary comprehension. And at the singularity at its center, where the curvature formally becomes infinite, the equations of general relativity stop making meaningful physical predictions altogether. Something else must govern that regime. Physicists suspect it requires a complete theory of quantum gravity, which does not yet exist in a confirmed form. Time does not escape this curvature. This is one of the most disorienting results of 20th century physics, and it is not speculative. Clocks run at different rates depending on where they are in a gravitational field. The deeper inside a gravitational well a clock sits, the more slowly it ticks relative to a clock far away. This effect, gravitational time dilation, has been measured directly. In 1976, the Gravity Probe experiment launched a hydrogen maser clock to an altitude of roughly 10,000 kilometers and compared its rate to an identical clock on the ground. The orbiting clock ran faster, as predicted, by about 4 parts in 10 to the 10th per second. The prediction of general relativity matched the observation to better than 1 part in 10,000. The GPS satellite network depends on this correction every day. GPS satellites orbit at roughly 20,000 kilometers altitude. From that altitude, their atomic clocks run faster than ground-based clocks by about 45 microseconds per day due to the weaker gravitational field. This is partially offset by a slower rate from their orbital velocity, a different relativistic effect. But the net result is that GPS clocks would drift by roughly 38 microseconds per day relative to ground clocks if uncorrected. 38 microseconds translates to a position error of about 11 kilometers per day. The correction is built into the system. Without it, every GPS receiver on Earth would give increasingly wrong coordinates, drifting further from reality with every passing hour. At the surface of our Sun, clocks run slower than they do on Earth by about 2 microseconds per day. Near the event horizon of a black hole, the disparity is not measured in microseconds. It is measured in the relationship between finite time at the horizon and effectively infinite time elsewhere. The second source of relativistic time dilation operates independently of gravity. Velocity also affects the rate at which clocks tick. A clock moving at high speed through space runs slower than an identical clock at rest, by a factor that grows without limit as the speed approaches the speed of light. At 10% of the speed of light, the dilation is about 0.5%. At 90% of the speed of light, moving clocks run at less than half the rate of stationary ones. At 99% of the speed of light, the factor is roughly 7. A year of travel corresponds to 7 years elapsed for those left behind. This is not an illusion, not a perspective effect. The asymmetry is real. The traveling clock returns with less elapsed time. This asymmetry is at the heart of what is sometimes called the twin paradox. 2 twins, one remains on Earth, one departs on a high-speed journey and returns, because the laws of physics are the same in all inertial reference frames. It might seem like neither twin can be said to have truly moved, motion being relative. But the twins are not equivalent. The traveling twin has to accelerate to leave, turn around, and return. Acceleration breaks the symmetry. The traveling twin experiences a non-inertial reference frame. The earthbound twin does not. When they reunite, the traveler is younger. By how much depends on the speed and duration of the journey. At the speed achieved by the New Horizons spacecraft, roughly 67,000 kilometers per hour, the relativistic dilation is negligible. A journey of 1,000 years would produce a time difference of perhaps a few hours. But at 99% of the speed of light, a round trip to the Andromeda Galaxy, about 2.5 million light years, would take roughly 5 million years as measured by Earth, but only about 700,000 years as experienced by the traveler. The galaxy they return to would be unrecognizable. 5 million years is approximately the length of time since the earliest members of the human genus walked upright. Gravitational and velocity-based time dilation combine in real systems. An atomic clock flown around Earth on a commercial aircraft runs slow compared to a ground clock due to its velocity, but runs fast due to its higher altitude and weaker gravitational field. The two effects partially cancel, but not completely. The net result has been measured repeatedly since 1971, when physicists Hafele and Keating flew cesium atomic clocks around the world on commercial flights and compared them to reference clocks at the US Naval Observatory. The results matched the predictions of both special and general relativity to within the experimental uncertainty. Time dilation is not a theoretical abstraction. It is a measured feature of reality that every accurate clock on Earth accounts for. If you were to hover just outside the event horizon of Cygnus X1, a black hole system, roughly 6,000 light years from Earth, estimated at around 21 solar masses, held in place by an engine of sufficient thrust, an observer far away watching you through a telescope would see your movement slow, light leaving you would become increasingly redshifted, its wavelength stretching as it climbed out of the gravitational potential. As you approach the event horizon itself, from the distant observer's perspective, you would appear to freeze. The redshift would become total. The image of you at the threshold would fade from view, dimming asymptotically, never quite arriving at the moment of crossing. From your own perspective, however, crossing the event horizon would feel like nothing in particular. There is no local marker, no sign, no wall. You pass through a mathematical boundary in empty space. And then the character of space-time itself changes in a way that has no analogy in ordinary experience. Inside the event horizon, the direction toward the singularity acquires the same character as the direction toward the future. Just as you cannot choose to stop moving into the future outside a black hole, inside the event horizon you cannot choose to stop moving toward the singularity. The geometry has rearranged itself. The singularity is not a place you fall toward. It is a time you approach. This is the sense in which time inside a black hole becomes spatial, and it is why nothing escapes. There is no trajectory that leads outward. All futures point inward, but the story does not end at the event horizon. In 1974, Stephen Hawking combined general relativity with quantum field theory and arrived at an unexpected result. When quantum mechanical effects are incorporated into the analysis of space-time near an event horizon. The horizon is not perfectly dark. Pairs of virtual particles, which quantum mechanics permits to spontaneously appear from the vacuum of empty space, are created continuously near the horizon. Occasionally, one member of a pair falls inward while the other escapes outward as real radiation. This radiation, now called Hawking radiation, carries energy away from the black hole. Over enormously long timescales, the black hole loses mass and eventually evaporates entirely. For a stellar mass black hole, the evaporation timescale exceeds the current age of the universe by many orders of magnitude. The effect is unobservably small with current instruments, but its theoretical implications are profound. If a black hole can evaporate what happens to the information that fell into it? The matter that formed the black hole and everything that subsequently fell in carried quantum information, the specific quantum states of every particle. Hawking radiation, in his original formulation, appears to be thermal and featureless. It carries no record of what fell in. This means information would be permanently destroyed at the moment the black hole evaporates completely. But the destruction of information violates a foundational principle of quantum mechanics. The apparent contradiction between Hawking's result and quantum theory has been called the black hole information paradox, and it remains one of the deepest unresolved problems in theoretical physics. The depth of the paradox was sharpened considerably in 2012 when a group of physicists, Ahmed Almheiri, Donald Merolf, Joseph Polchinski, and James Sully, published what became known as the AMP-IS paper after their initials. They show that three individually reasonable assumptions about black holes cannot all be true simultaneously, that quantum mechanics is valid everywhere, that an infalling observer experiences nothing unusual at the event horizon, and that information escapes in the Hawking radiation. At least one of these must fail. If information escapes, the radiation must be entangled with the interior in a way that creates a violent boundary, a firewall of energetic quanta at the horizon that would incinerate any infalling observer. The smooth, uneventful horizon crossing, which had seemed so clear from the mathematics of general relativity, might in fact be the most catastrophic transition in physics. The alternative proposed by Leonard Susskind and Gerard 't Hooft, black hole complementarity, argues that the paradox is an illusion arising from assuming that two observers, one inside and one outside the horizon, could compare notes. In practice, they cannot. The infalling observer crosses smoothly. The distant observer sees the information emerge encoded in the Hawking radiation. Both descriptions are internally consistent. The contradiction only appears if you try to combine the views of both observers simultaneously, which requires transmitting information faster than light, something prohibited by the physics itself. Complementarity does not so much solve the paradox as argue that it is not a real paradox for any single observer. More recent progress has come through the calculation of what physicists call the Page curve, the predicted evolution of the entanglement entropy of Hawking radiation over the lifetime of an evaporating black hole. In 2019 and 2020, several groups independently showed, using techniques from the AIDS CFT correspondence and quantum extremal surfaces, that the Page curve can be reproduced. The entanglement entropy initially rises and then falls, consistent with information eventually escaping rather than being permanently lost. The calculation involves contributions from a new class of saddle points in the gravitational path integral, dubbed replica wormholes, which allow information to leak out through quantum gravitational effects at very late times. Whether this calculation fully resolves the paradox or merely reformulates it is a question that physicists continue to debate. Now look away from the black holes at the scale of the observable universe. Pull back until individual galaxies become points of light, and the large-scale architecture becomes visible. At this scale, hundreds of millions to billions of light years, the universe is not a uniform fog of evenly distributed matter. It has structure, coherent filamentary, foam-like structure. Gravity has spent 13 billion years sorting matter into this pattern. The densest regions drew in gas and dark matter, which collapsed into galaxies and galaxy clusters. Between the clusters, vast, nearly empty regions called voids stretch for hundreds of millions of light years. The Bourtes void, discovered in 1981, spans roughly 330 million light years. At the time of its discovery, its emptiness seemed almost implausible. Statistical models of galaxy formation predicted that a void of that size should contain several thousand galaxies. The observed count was initially around 60. The void is real, and its existence reflects the way gravity amplifies small initial densities, pulling matter out of some regions and concentrating it into others. Leaving the evacuated volumes behind. Between the voids, the clusters are connected by long bridges of galaxies and gas, the cosmic filaments. The whole arrangement resembles at sufficient scale a three-dimensional sponge, the cosmic web. Our own galaxy, the Milky Way, sits within the local group, a modest collection of about 50 galaxies. The local group is gravitationally bound to the Virgo cluster, which is part of the larger Laniakea supercluster, a structure roughly 520 million light-years across, containing the mass of approximately 100 million billion suns. Laniakea itself flows gravitationally toward a concentration known as the Great Attractor, a region of excess mass density in the direction of the constellations Centaurus and Hydra, roughly 150 million light-years away, whose full nature remains incompletely characterized. Among the largest known coherent structures in the cosmic web is the Hercules Corona Borealis Great Wall, detected through the statistical distribution of gamma-ray bursts across a region of sky. It spans an estimated 10 billion light-years in its longest dimension. To put that number into a frame that might carry some weight, light, traveling at approximately 300,000 kilometers per second, would require 10 billion years to cross it. That is longer than the age of the Earth, longer than the time that has passed since complex multicellular life first appeared. It is a structure so large that its existence challenges the cosmological principle, the foundational assumption that matter is distributed uniformly across space when viewed at sufficient scale. The Sloan Great Wall, identified in 2003 from data gathered by the Sloan Digital Sky Survey, stretches approximately 1.37 billion light-years and sits roughly a billion light-years from Earth. It is composed of galaxy superclusters arranged in a flattened sheet, with voids surrounding it on either side. The filaments bounding those voids are not empty. They contain dark matter, whose gravitational influence determines the shape of the web, even in regions where luminous matter is absent. Dark matter does not emit, absorb, or scatter light. Its presence is inferred entirely from the gravitational effects it produces on the matter we can see, and from the lensing distortions it imprints on background light. It constitutes roughly 27% of the total energy content of the observable universe. What it physically is, which particle or particles compose it, remains unknown. The leading candidates have changed over decades as experiments have progressively ruled out possibilities for many years. The most favored hypothesis was the weakly interacting massive particle, or WIMP, a hypothetical particle with a mass in the range of 10 to 1,000 times the proton mass, interacting with ordinary matter only through the weak nuclear force and gravity. WIMPs were theoretically attractive because supersymmetric extensions of the standard model of particle physics naturally predict such particles with properties in the right ballpark to explain the observed dark matter density, a coincidence called the WIMP miracle. Dedicated underground experiments designed to detect the rare collisions between WIMPs and atomic nuclei operated for decades at exquisite sensitivity. The most sensitive, including Lux Zeppelin in South Dakota and Pandax in China, have now excluded large portions of the predicted WIMP parameter space without detecting any candidates. The WIMP miracle has not been ruled out, but it is under significant pressure. Alternative candidates include axions, extremely light particles originally proposed in 1977 to solve a different problem in particle physics, the strong CP problem, and later recognized as viable dark matter candidates, if they are abundant enough. Axion searches have intensified significantly in recent years. The ADMX experiment, using a tunable microwave cavity immersed in a strong magnetic field, searches for the tiny photons that axions would produce when converting in the presence of a magnetic field. Sensitivity has improved to the point where theoretically motivated axion masses are being probed for the first time. A third possibility, which requires no new particle physics at all, is that dark matter consists of compact objects, primordial black holes formed in the early universe before any stars existed. If density fluctuations in the first fraction of a second after the Big Bang were large enough in localized regions, those regions could have collapsed directly into black holes without passing through any stellar phase. Primordial black holes, spanning a wide range of masses, from asteroid mass to many solar masses, could in principle constitute a fraction or all of the observed dark matter. The gravitational wave detections by LIGO, which found black hole mergers at masses not easily explained by standard stellar evolution, briefly revived interest in this possibility. Current constraints from gravitational microlensing surveys, the cosmic microwave background, and the absence of X-ray emission from accreting primordial black holes significantly limit but do not eliminate the parameter space. Whether dark matter is a particle, a primordial black hole, or something else entirely remains one of the most consequential open questions in physics. These structures were not placed. They grew. The initial conditions of the early universe, quantum fluctuations in density, amplified by the expansion of space and the attractive pull of gravity, seeded every filament, every void, every supercluster visible today. The cosmic web is the frozen, slowed-down echo of quantum events that occurred in the first fractions of a second after the Big Bang. The most direct snapshot of those initial conditions is the cosmic microwave background radiation. In the first few 100,000 years after the Big Bang, the universe was hot and dense enough that matter and radiation formed a single interacting plasma. Photons could not travel freely. They were continuously scattered by the charged particles around them. Then, as the universe expanded and cooled to about 3000 Kelvin, electrons combined with protons to form neutral hydrogen atoms. The plasma became transparent. Light was free to travel for the first time. The photons released at that moment have been traveling since, stretched by the expansion of space to microwave wavelengths. We detect them today as a nearly uniform glow arriving from every direction, with a temperature of 2.725 Kelvin, just under 3 degrees above absolute zero. The word nearly is critical. The cosmic microwave background is not perfectly uniform. Mapped to high precision by the COPE satellite in the early 1990s, and then by Dublium MAP and Planck in subsequent decades, it shows temperature fluctuations of about 1 part in 100,000. These tiny variations represent the density fluctuations of the early plasma regions that were slightly hotter, slightly denser than their surroundings. Those regions went on to collapse under gravity and become the seeds of the cosmic web. The pattern of fluctuations carries the fingerprints of the physics active in the first fraction of a second. The initial spectrum set by a period of exponential expansion called inflation, and then modified by acoustic oscillations in the plasma as matter and radiation sloshed together for hundreds of thousands of years. Those acoustic oscillations left a permanent imprint in the distribution of matter. A preferred separation distance, approximately 490 million light-years in today's universe, exists between galaxy pairs, corresponding to the distance sound could travel in the primordial plasma before it froze at recombination. This feature, called the baryon acoustic oscillation scale, acts as a cosmic ruler. By measuring the characteristic separation of galaxies at different epochs, cosmologists can trace the expansion history of the universe. The baryon acoustic oscillation signal has been detected in galaxy surveys, quasar distributions, and the cosmic microwave background itself. and it represents one of the most powerful tools in modern precision cosmology. The consistency of the measurements across multiple independent methods provides strong confirmation that the basic picture, a universe born hot, expanding and cooling, with structures seeded by quantum fluctuations, is correct in its broad strokes. Inflation, the brief period of exponential expansion proposed by Alan Guth in 1980 and refined by André Linde and others, explains why the cosmic microwave background is so nearly uniform across regions of sky that should not have been in causal contact with each other by the time the light was emitted. Inflation stretched quantum fluctuations to cosmic scales, smoothing large-scale anisotropies while preserving the small-scale variations that seeded structure. The precise spectrum of those fluctuations, measured in the microwave background, is consistent with the simplest inflationary models. But inflation itself remains a theoretical framework without a confirmed physical mechanism. The identity of the inflaton field that drove the exponential expansion is unknown, and the energy scale at which inflation occurred has not been directly measured. Now consider time again, not the time that bends near a black hole, but the time you experience every day. The time that divides your life into before and after, the time that moves, it seems, in only one direction, at only one rate, and without your consent. Suppose for a moment that time stopped, not slowed, not dilated the way relativity allows, but stopped entirely, froze. The universe converted from a film to a single frame. The physical consequences arrive before any pleasant fantasy does. The electrochemical processes that constitute thought depend on ions moving across neural membranes, on molecules shifting through cellular structures. Motion requires time. Without time, neurons cannot fire. Consciousness ceases before the thought of enjoying the pause can be completed. The air in your lungs cannot be exhaled because exhaling requires motion, which requires time. Sound cannot travel because sound is a compression wave, and waves require propagation through time. The thermodynamic processes that keep the body warm stop cold. Light itself, the means by which vision works, is a wave oscillating in time. Without time, there is no oscillation, there is no photon in transit. The world does not go dark. It simply never produces another image at all. Consider the quantum dimension of this impossibility. In quantum mechanics, the state of every particle in the universe is described by a wave function that evolves continuously in time, according to the Schrödinger equation. The wave function is not a static object, it is a process. It is defined by its change. Remove time and the wave function does not freeze at some definite configuration. It ceases to be a valid physical description at all. The universe is not a set of particle positions that could in principle be paused mid-arrangement. It is a dynamic field of quantum amplitudes whose physical meaning is constituted by their ongoing evolution. Stopping time does not halt the universe. It removes the condition under which the universe has any definite state at all. If you relax the constraint, if you allow yourself to exist within the pause while the rest of the universe obeys it, a different problem emerges. You are moving through a universe in which light is frozen. Every photon in the air around you is stationary. The moment you take a single step, you are moving relative to those photons. But nothing can move faster than light. Your first step would make you superluminal relative to the frozen electromagnetic field. The energy required to do this would be, according to relativistic mechanics, effectively infinite. The mass of your body would approach infinity. What actually happens in any physically grounded scenario, you do not step, you cannot. The frozen universe is not a stage you can walk across. It is a prison in which even the concept of motion becomes self-contradictory. What the thought experiment reveals is that time is not a container in which physics happens. Time is woven into the structure of physics. Removing it does not leave the universe intact and paused. It removes the universe. But the thought experiment raises a further puzzle. The fundamental equations of physics, Newton's laws, Maxwell's equations, Schrödinger's equation, Einstein's field equations, are all time-symmetric. Run them forward, and they produce valid physical evolution. Run them backward, and they produce equally valid solutions. Nothing in the fundamental laws distinguishes the past from the future, and yet experience is not time-symmetric. Broken glass does not reassemble. Heat does not spontaneously flow from cold objects to hot ones. The past feels permanently fixed, while the future remains open. This asymmetry, the arrow of time, is one of the genuinely deep puzzles of physics. The standard answer points to entropy. The second law of thermodynamics states that in any closed system, entropy, the measure of disorder, or more precisely, the number of microscopic configurations consistent with the observed macroscopic state, tends to increase or remain constant over time. A glass shatters because there are vastly more disordered configurations of glass fragments than intact glass configurations. The reverse process is not forbidden by any law. It just requires all the fragments to spontaneously coordinate their motion, which has a probability so low it is effectively zero. Entropy increases because there are many more ways for a system to be disordered than to be ordered. But this answer only relocates the question: why was entropy ever low to begin with? If the laws of physics are time-symmetric, there is nothing in the physics that required the early universe to be in a low entropy state. And yet, it was extraordinarily so. The cosmic microwave background is uniform to 1 part in 100,000, a state of near-perfect homogeneity that represented an extremely low entropy for a system of that energy. The expansion of the universe from that state, the gradual condensation of matter into stars, galaxies, and black holes as gravity pulled density fluctuations together, is itself the entropy increasing process from which the arrow of time derives. The direction of time that we experience is, in this view, inherited from the thermodynamic direction of the universe, from the extraordinarily improbable initial state of the Big Bang toward the maximally disordered future of cold, dark, empty space. The physicist Roger Penrose has argued that the initial low entropy of the universe requires explanation beyond the standard inflation story, since inflation itself, while smoothing geometric curvature, does not reduce the gravitational degrees of freedom in the way the low entropy initial condition requires. His proposed resolution, conformal cyclic cosmology, imagines the universe as one of an infinite sequence of aeons, each beginning with a Big Bang and ending in a featureless de Sitter expansion, with the ending state of one aeon mathematically matching the beginning state of the next. It is a speculative framework, but it takes seriously the thermodynamic asymmetry as a fundamental feature of the universe's history rather than a coincidence. This leads naturally to a deeper question. What is time, structurally? And what are the laws that govern its behavior? General relativity treats time as a dimension distinguishable from the 3 spatial dimensions only by a sign in the equations, a sign that encodes the fact that we can move freely in space, but only forward in time. Quantum mechanics, the framework that describes the behavior of matter at the smallest scales, treats time differently, as an external parameter, a background against which quantum systems evolve. The 2 frameworks are incompatible at the foundational level. They cannot both be entirely right. Physicists have known this since the 1920s and have been working on the problem ever since. Several approaches to quantum gravity exist. String theory replaces point particles with one-dimensional vibrating strings and requires additional spatial dimensions beyond the 3 we observe. the number of mathematically consistent string vacua, different configurations of the extra dimensions that each produce a different low-energy physics, may be astronomically large, possibly as large as 10 to the power of 500. This landscape of string vacua has prompted some physicists to invoke entropic reasoning. We observe the physics we do because we inhabit a region of the multiverse where the laws permit our existence. Others consider this an abandonment of the scientific program, since a theory that accommodates any observed value of any constant explains nothing about why those values are what they are. Loop quantum gravity proposes that space itself is not continuous but composed of discrete, quantized units called spin networks. On scales smaller than the Planck length, approximately 10 to the negative 35th meters, 17 orders of magnitude smaller than a proton. Space is not a smooth continuum, but a granular structure, like a fabric seen close enough to reveal individual threads. Time, in loop quantum gravity, is also discrete. It evolves in finite steps rather than flowing continuously. The equations of loop quantum gravity applied to the early universe, a field called loop quantum cosmology, suggest that the Big Bang singularity is replaced by a big bounce, a preceding phase of contraction that reaches a maximum density and then rebounds into expansion. The singularity is regularized by the discreteness of the geometry. Whether this prediction can be tested observationally, for example through specific signatures in the cosmic microwave background, is an active area of investigation. Causal dynamical triangulations attempt to build spacetime from elementary simplices that assemble according to causal rules. Each approach has successes in restricted domains and difficulties that have so far prevented experimental confirmation. A subtler problem underlies all of these approaches, the problem of time in quantum gravity. In ordinary quantum mechanics, time is a fixed external parameter. The Schrödinger equation describes how a system evolves in time, where time is taken from an external clock, unaffected by the system. In general relativity, there is no preferred external time. The equations are generally covariant. They look the same in any coordinate system, including any choice of time coordinate. When you attempt to combine the two frameworks and write a quantum equation governing the entire universe, including all possible time coordinates, the time parameter disappears from the equation altogether. The Wheeler-DeWitt equation, derived in the 1960s, describes the quantum state of the universe, but contains no explicit time. Time, in the quantum mechanical sense, does not appear as a fundamental quantity. It must somehow emerge from the relationships between different parts of the quantum state of the universe, a phenomenon called the emergence of time, which has no satisfactory derivation in any existing framework. One recent and unconventional proposal suggests that this incompatibility might be resolved by reconsidering what the universe fundamentally is. In this framework, the universe is treated as an analog of a neural network, a system of interconnected elements that process information and adapt. The claim is not that the universe is conscious or that it thinks. The claim is mathematical, that the dynamics of certain neural networks under specific training conditions naturally reproduce behaviors analogous to both quantum mechanics and general relativity as emergent phenomena. In this picture, space-time and quantum fields are not the foundational ingredients of physics. They are outputs. They arise from the learning dynamics of a more fundamental underlying structure. This connects to a broader idea in theoretical physics, the holographic principle. In 1972, Jacob Bekenstein showed that the entropy of a black hole, the measure of information content associated with its interior, is not proportional to its volume as classical thermodynamics would suggest, but to the area of its event horizon. Hawking confirmed this result and refined it. The implication is strange. The information content of a three-dimensional region of space can be fully encoded on a two-dimensional surface bounding that region. The universe, or at least a region of it, might be equivalent in information content to what can be written on its boundary. This principle has been developed most concretely in the anti-de Sitter conformal field theory correspondence proposed by Juan Maldacena in 1997. The correspondence shows that a specific theory of quantum gravity in a certain geometry is mathematically equivalent to a quantum field theory living on the boundary of that geometry, one dimension lower. The two descriptions are dual, different mathematical languages for the same physical system. Whether this duality applies to the observable universe, which has a different geometry than the one Maldacena worked with, remains an open question. But the implication that information, not matter or energy, may be the foundational currency of physical reality has not gone away. Whether any of these frameworks will produce the unified theory of gravity and quantum mechanics that physics requires is precisely what the science of the next century will have to determine. In April 2019, a result arrived that had seemed for decades to be permanently beyond reach. The Event Horizon Telescope collaboration, a network of 8 radio observatories distributed across 5 continents, coordinated to function as a single dish with an effective aperture the size of Earth, released an image. It showed the center of Messier 87, a giant elliptical galaxy 55 million light-years away. At the center of that image, a bright, irregular ring of hot plasma, and within the ring, a dark, circular region. The dark region is the shadow of the black hole. Light bending around the event horizon creates the glowing ring. The darkness is not the black hole itself. The black hole has no visible surface, but the region from which no light escapes toward the observer. The mass of the object producing this shadow is approximately 6.5 billion times the mass of the Sun. The technical achievement required to produce this image was extraordinary. Radio telescopes at different sites collected data simultaneously, synchronized to atomic clocks, accurate to within a fraction of a nanosecond. The data volume was so large, petabytes per site, that it could not be transmitted electronically. Physical hard drives were flown from each observatory to central processing facilities, where the signals were correlated using a technique called very long baseline interferometry. The angular resolution achieved was equivalent to resolving an object the size of an orange on the surface of the Moon. A second image followed the same black hole, this time imaged in polarized light. Polarization reveals the orientation of electromagnetic fields. In the new image, the magnetic field lines around the black hole became visible for the first time, a structured spiraling architecture in the plasma. Confirming that magnetic turbulence plays a central role in the dynamics of how black holes consume matter and eject it as jets into intergalactic space. The jet from M87 extends roughly 5,000 light-years from the nucleus. Its base had been imaged previously. Now, for the first time, astronomers could see both the launch mechanism and the launcher simultaneously. In 2022, the same collaboration released an image of a second black hole, Sagittarius A star, the 4 million solar mass black hole at the center of our own galaxy, about 26,000 light-years from Earth. Imaging it required far faster processing techniques because the plasma near Sagittarius A star changes on timescales of minutes due to the smaller size of the object. The equivalent of trying to photograph something that is blurring itself faster than the exposure allows. Algorithms had to reconstruct the image by averaging over many exposures, each captured at a slightly different state of the turbulent plasma. 2 images of 2 very different black holes, 2 wildly different mass scales. The same geometry in both, a bright ring, a dark center. The physics of general relativity confirmed at both ends of the mass spectrum. The question those images cannot answer is how the two mass scales connect. Stellar mass black holes form when stars above roughly 20 solar masses exhaust their nuclear fuel and collapse. The collapse compresses the core beyond the density at which neutron degeneracy pressure can resist gravity. The core implodes. The outer layers rebound in a supernova. What remains is a compact object whose mass is measured in tens of solar masses. Supermassive black holes, like the one in M87, have masses billions of times larger than that. How did they grow so large? One mechanism is direct collapse. In the early universe, conditions may have allowed massive gas clouds to collapse without forming stars, producing objects of 10,000 to 100,000 solar masses directly. Another is sequential merging. Smaller black holes brought together by the dynamics of dense star clusters or galaxy mergers combine over time into progressively larger objects. The intermediate stages of that growth, objects in the range of thousands to hundreds of thousands of solar masses, had never been directly confirmed as a class. In 2015, the LIGO gravitational wave detector made its first detection, a signal lasting a fraction of a second, encoding the merger of two black holes of approximately 36 and 29 solar masses, producing a single black hole of around 62 solar masses. The remaining mass, about 3 solar masses, was radiated away as gravitational waves in under a second, briefly outpacing the energy output of every star in the observable universe combined. The detection opened an entirely new observational window. The universe suddenly had a voice, or rather, physicists had built ears capable of hearing it for the first time. In 2020, analysis of gravitational wave data revealed an intermediate mass event. A merger between a black hole of about 85 solar masses and one of about 66 solar masses, producing an object of about 142 solar masses. The result lay squarely in the mass range that stellar evolution models suggest should be nearly empty, a region where pair instability supernovae are predicted to disrupt stars before they can collapse. An intermediate mass black hole sitting at 142 solar masses implies formation pathways that are not yet fully understood. If such objects exist in sufficient numbers, they represent precisely the missing evolutionary link between stellar and supermassive black holes. Now consider approaching one. Not the supermassive kind, the tidal forces near Sagittarius A star at the event horizon are actually mild enough that a person might survive crossing, at least briefly, because tidal forces scale with mass differently than horizon radius. Consider instead a stellar mass black hole of 30 solar masses, roughly 7 times the gravitational radius of the Sun, with an event horizon about 88 kilometers in diameter. From a great distance, the black hole is invisible. The space around it appears undistorted. The stars behind it are where they should be. As you approach, the distortion begins to grow. Light from stars that should be behind the black hole begins to appear around its edges, bent by the gravitational field redirected toward you. The region of sky from which light comes starts to compress. The black hole itself appears to grow faster than simple geometry would predict, because you're not just getting closer. The curvature of space is increasing the effective distance between each step and the center. At a certain distance, roughly 1.5 times the Schwarzschild radius, you reach the photon sphere. This is the radius at which photons travel in circular orbits. The orbits are unstable. Any slight perturbation sends the photon spiraling inward or outward. At this distance, looking directly perpendicular to your direction of motion, you could see the back of your own head, light that left you, curved around the black hole and returned from the other side. Multiple images of yourself are visible, each one representing light that completed a different number of orbits around the black hole before reaching your eyes. Looking forward toward the black hole, you see only darkness. No light reaches you from that direction because none originates from that direction that can escape the curvature. The universe behind you, conversely, is compressed into a shrinking disk as you approach the event horizon. This disk brightens and blue shifts more and more radiation, originally infrared or radio, becomes visible light, then ultraviolet, then X-ray. The entire electromagnetic history of the observable universe is being gathered and focused on the shrinking window behind you. The tidal forces, the differential gravity between your head and your feet, begin to matter at stellar mass black holes. The gradient of gravity across a human body becomes lethal before the event horizon is reached. This process has been given the name spaghettification. The body is stretched along the radial direction and compressed laterally, because the gravitational pull on the near side is stronger than on the far side, and both are stronger than the lateral pull. The larger the black hole, the gentler the tidal gradient at the horizon, because the horizon is farther from the singularity where gravity is most intense. For Sagittarius A star, the tidal forces at the horizon are survivable. For a 30 solar mass black hole, they are not. The accretion disk surrounding the black hole, if one is present, has its own visual drama. The disk is not a flat ring seen edge-on, as it is often depicted. Gravitational lensing bends the light from the far side of the disk up and over the black hole, and the light from the near side of the disk around and under it. From the right vantage, you can see the entire disk simultaneously. The top surface of the far side appears above the shadow, and the bottom surface of the far side appears below it, wrapped around the shadow like a luminous frame. The image is further distorted by the relativistic motion of the plasma. The side of the disk rotating toward you appears far brighter than the side rotating away. This relativistic Doppler beaming, the compression of radiation toward the direction of motion, concentrates the luminosity asymmetrically. In the first real image of a black hole, M87, the southern arc of the ring is noticeably brighter than the northern arc for exactly this reason. The plasma in the inner disk, orbiting at relativistic velocities and compressed to temperatures of billions of Kelvin, radiates across the entire electromagnetic spectrum. In X-ray binaries, systems where a stellar mass black hole strips material from a companion star, the inner accretion disk produces X-ray luminosities that can rival small galaxies. The material approaching the innermost stable circular orbit, beyond which it plunges inward without further orbiting, reaches velocities that are a substantial fraction of the speed of light. At that final orbit, general relativistic effects are dominant. The location of the innermost stable circular orbit depends on the spin of the black hole. For a non-rotating Schwarzschild black hole, it sits at 3 times the Schwarzschild radius. For a maximally rotating Kerr black hole, the ergosphere extends it inward until it nearly coincides with the event horizon itself, allowing the accreting material to release a much larger fraction of its rest mass energy as radiation. A maximally spinning black hole is in this sense the most efficient energy converter in the known universe. Then comes the crossing. There is no physical sensation at the crossing of the event horizon itself. No barrier, no boundary, no change in the local laws of physics. But from this point, the geometry has changed character. The singularity is now in your future. And just as you cannot move backward in time, you cannot move away from it. Any thrust you apply in any direction accelerates you toward it. The inside of the event horizon is not a place. It is a period of time with a beginning, the crossing, and an end, the singularity, and no spatial freedom that could change either. What you would see in that final interval is an open question. The equations do not provide a clear phenomenology for an observer inside. The singularity itself is the location where the equations break. Something happens there that general relativity cannot describe. Whether quantum effects smooth the singularity into something physically finite, a Planck density core perhaps, or whether the singularity represents a genuine breakdown of space-time. No confirmed theory answers. The mathematics of general relativity, extended beyond what physical realism requires, permits a peculiar mirror image of a black hole. If you draw the complete Penrose diagram of the Schwarzschild solution, a conformal map of the entire spacetime, you find 4 regions, not 2. There is the exterior region familiar from observation. There is the black hole interior, bounded by the future singularity, but the time-reversed structure also appears, a white hole bounded by a past singularity from which matter emerges, but into which nothing can enter. And connecting the exterior region of the black hole to an entirely separate exterior region, possibly an entirely separate universe, is a bridge, the Einstein-Rosen bridge, commonly called a wormhole. In 1935, Einstein and Rosen noticed this structure in the Schwarzschild solution. They initially thought it might represent an elementary particle, a particle as a geometrical feature of space-time rather than a separate entity inserted into it. That idea did not survive contact with quantum mechanics. But the bridge structure remained. The Schwarzschild wormhole is not traversable. Its throat collapses faster than any signal traveling at the speed of light could cross it. Nothing can get from one side to the other. The wormhole is a geometrical feature of the solution, but a useless one for any purpose that requires physical travel. Rotating black holes described by the Kerr metric are more interesting. Their Penrose diagrams show an infinite series of connected universes, and the inner horizon of a Kerr black hole may be traversable in the idealized mathematical case. But the inner horizon is unstable. Any perturbation, any infalling radiation, causes it to collapse into a singularity of its own, called a mass inflation singularity. The idealized mathematical wormhole is destroyed by anything you add to the system to traverse it. The deep connection between wormholes and quantum entanglement has been proposed in what physicists call the ER equals EPR conjecture, put forward by Juan Maldacena and Leonard Susskind in 2013. EPR refers to the Einstein-Podolsky-Rosen paper of 1935, which described quantum entanglement, the phenomenon by which two particles can be correlated regardless of the distance between them, in a way that cannot be explained by classical hidden variables. ER refers to the Einstein-Rosen bridge. The conjecture proposes that these are the same phenomenon, that two entangled particles are connected by a microscopic, non-traversable wormhole, and that the geometry of spacetime itself might be stitched together from the quantum entanglement of its constituent degrees of freedom. Entanglement is the thread from which the fabric of space is woven. This is still a conjecture, not a theorem, and its full implications are being actively developed. But it suggests that the most fundamental questions about gravity, about space-time geometry, about black holes, about the nature of singularities, may ultimately be questions about quantum information. Look now not at the deaths of individual stars collapsing in isolation, but at what happens when stars find each other. The universe is not a static backdrop of fixed points. Every star in the galaxy is moving, orbiting the galactic center, drifting relative to its neighbors, caught in the gravitational dynamics of its local environment. Over long enough timescales, at sufficient stellar densities, stars collide. The environments where this happens most frequently are globular clusters, ancient, gravitationally compact collections of hundreds of thousands to millions of stars, packed into regions only a few hundred light years across. The density of stars at the center of a globular cluster can exceed tens of thousands per cubic light year compared to the solar neighborhood, where the nearest star to our sun is over 4 light years away. In such environments, close stellar encounters and direct collisions occur at rates estimated at roughly once per 10,000 years per cluster. Across the galaxy's approximately 150 known globular clusters, this adds up to a measurable rate of stellar mergers happening right now in the present epoch. The outcome of a stellar merger depends on the masses and evolutionary states of the stars involved. Sometimes the prelude to merger is observed. In January 2002, the star V838 Monocerotis, located about 20,000 light-years away in the constellation Monoceros, underwent an outburst that temporarily made it the most luminous star in the Milky Way. Its brightness increased by a factor of about 10,000 over the course of several weeks. When the light echo, a shell of reflected light expanding outward through surrounding dust, was imaged by the Hubble Space Telescope. The event became one of the most photographed phenomena in modern astronomy, revealing concentric rings and filaments sculpted by decades of previous stellar wind activity. The leading explanation is a stellar merger, two stars in a binary system spiraling together and coalescing, releasing their gravitational binding energy in a luminous outburst. The resulting object, a bloated reddened merged star, is still observable. Cooling slowly, even stranger is the case of Eta Carinae, a massive binary system about 7,500 light-years away. In the 1840s, Eta Carinae underwent what is called a great eruption, briefly becoming the second brightest star in the night sky, despite being invisible to the naked eye from most of the planet. Over several years, it ejected approximately 10 solar masses of material, which formed the Homunculus Nebula, a double-lobed shell of gas and dust visible to this day. The system survived. Both stars remained surrounded by their ejected envelope. Whether the eruption was driven by a near merger, by a triple star interaction, or by some other instability in a star operating near the theoretical limits of luminosity is still debated. Eta Carinae is now classified as a luminous blue variable, a rare class of massive stars undergoing periodic eruptions. Its combined luminosity is approximately 5 million times that of our Sun. When it eventually dies, in an event that may be a hypernova or a directly collapsed black hole, it will be among the most energetic stellar deaths the galaxy has witnessed in recorded history. When two main sequence stars still fusing hydrogen in their cores, collide and merge, the product is a single, hotter, more luminous star with a mass equal to the combined mass of its progenitors, minus whatever was ejected during the collision. These objects, called blue straggler stars, appear anomalously young and hot relative to the other stars in the cluster. They were identified and named long before their formation mechanism was understood. They look like stars that somehow fail to age normally. The explanation is merger. They absorbed a companion and reset their internal hydrogen supply, gaining an extended lifespan their original composition would not have allowed. When a white dwarf, the dense carbon-oxygen remnant of a low-mass star compressed to roughly Earth size and supported against collapse by electron degeneracy pressure, accretes mass from a binary companion, a different fate awaits. If the white dwarf gains sufficient mass to approach the Chandrasekhar limit of approximately 1.4 solar masses, the electron degeneracy pressure that supports it can no longer resist gravity. The white dwarf undergoes runaway carbon fusion, igniting from the center outward in a thermonuclear explosion that tears the star apart entirely. No remnant is left. The result is a type Ia supernova, one of the most standardizable and energetically consistent events in the universe, because their peak luminosity is tightly correlated with the rate at which they dim. Type Ia supernovae serve as standard candles, objects of known intrinsic brightness, whose distance can be calculated from observed brightness. They are the tool through which astronomers discovered, in 1998, that the expansion of the universe is accelerating. When two white dwarfs in a close binary system spiral together, their orbital energy radiated away as gravitational waves over millions of years. The merger may exceed the Chandrasekhar limit dynamically. The sudden mass overload triggers the same runaway fusion, producing a supernova from a completely different initial configuration. The distinction between these two formation channels, single degenerate and double degenerate, has significant consequences for the chemical enrichment of galaxies. White dwarf mergers contribute to the production of iron and other iron peak elements scattered through the interstellar medium. The mergers of neutron stars are in a different category entirely. Neutron stars are the remnants of stars heavier than about 8 solar masses that collapse after a supernova. They are approximately 20 kilometers in diameter, with densities comparable to an atomic nucleus, and they are composed almost entirely of neutrons packed to the limits of known physics. A single teaspoon of neutron star material would contain roughly 1 billion tons of mass on Earth's surface. When two neutron stars orbit each other in a tight binary, they too radiate gravitational waves and spiral inward. In August 2017, LIGO and its European counterpart Virgo detected gravitational waves from such a merger, the event catalogued as GW17817, occurring approximately 130 million light-years away. For the first time, the gravitational wave signal was accompanied by an electromagnetic counterpart, a short gamma-ray burst detected by the Fermi satellite 1.7 seconds after the merger, followed by a kilonova, an optical and infrared transient powered by the radioactive decay of heavy elements synthesized in the collision. That kilonova confirmed a long-standing theoretical prediction: neutron star mergers are the dominant site of rapid neutron capture nucleosynthesis, the process by which elements heavier than iron are built. Every atom of gold in a piece of jewelry, every atom of platinum in a catalytic converter, every atom of uranium in a nuclear reactor was forged in the collision of two neutron stars and scattered into space by the explosion. The merger of GW170817 alone is estimated to have produced several times Earth's mass in gold and comparable quantities of other heavy elements. These merged, spread through interstellar space, and became part of subsequent generations of stars and planetary systems, including eventually ours. Before considering that stranger merger, it is worth pausing on neutron stars themselves. The remnants of collapsed stellar cores, they are in many respects the most extreme objects in the universe that can still be studied with electromagnetic radiation. A neutron star of 1.4 solar masses, compressed into a sphere 20 kilometers across, has a mean density exceeding that of an atomic nucleus. The pressure at its center may be high enough to dissolve neutrons into their constituent quarks, forming a state of matter, quark-gluon plasma, that has not existed freely in the universe since the first microseconds after the Big Bang. Whether quark matter exists at neutron star cores or whether some other exotic phase dominates is a question that gravitational wave observations of neutron star mergers are beginning to constrain. Since the deformation of a neutron star during the inspiral phase before merger is sensitive to its internal structure, some neutron stars rotate with extraordinary speed. The fastest known pulsar, a neutron star, whose rotation produces a lighthouse-like beam of radio emission detectable each time it sweeps past Earth, completes 716 rotations per second. Its surface moves at a significant fraction of the speed of light. The stability of such rotation is itself remarkable. Pulsars are among the most accurate natural clocks in the universe, with rotational periods stable to better than 1 part in 10 to the 13th over years of observation. The pulsar timing array experiments, which monitor arrays of millisecond pulsars across the galaxy, exploit this stability to search for the gravitational wave background, the accumulated hum of gravitational waves from all the supermassive black hole mergers that have occurred throughout cosmic history. In 2023, several pulsar timing array collaborations simultaneously announced evidence for this background signal, opening a new frequency band in gravitational wave astronomy. A subset of neutron stars called magnetars possess magnetic fields roughly 1 trillion times stronger than Earth's and up to 1,000 times stronger than ordinary neutron stars. The energy stored in a magnetar's magnetic field is comparable to the total energy output of our Sun over 10,000 years. When the magnetar's crust shifts starquakes driven by the evolving magnetic field, it releases that energy in milliseconds as gamma ray and X-ray flares. On December 27, 2004, a magnetar designated SGR 180620 released a giant flare that, despite the source being 50,000 light-years away, briefly ionized Earth's upper atmosphere and saturated instruments on multiple gamma-ray satellites. Had that magnetar been 10 light-years away rather than 50,000, the flare would have been lethal at Earth's surface. The energy released in those few seconds was comparable to the total energy our Sun produces over 250,000 years. A stranger merger still is the theoretical object known as a Farn-Dushtkau object, proposed by Kip Farn and Anna Zhitkau in 1975. This hypothetical object forms when a neutron star becomes embedded inside a red supergiant. In a close binary system, the supergiant may expand during its late evolution to engulf the neutron star companion. The two objects become a single entity, a red supergiant with a neutron star at its center instead of a stellar core of fusing material. The energy source is accretion from the surrounding envelope onto the neutron star rather than nuclear fusion. The observable properties of such an object would resemble an ordinary red supergiant in most respects, with some unusual chemical signatures from nucleosynthesis processes that occur near the surface of the neutron star. In 2014, a candidate Thorne-Zhitkau object was identified in the Small Magellanic Cloud, a nearby satellite galaxy of the Milky Way, based on anomalous abundances of certain heavy elements in its spectrum. The identification remains tentative, awaiting further observational confirmation. Far from any black hole across billions of light years, another class of objects illuminate the early universe. Quasars, quasi-stellar objects, are the active nuclei of galaxies in the early universe, powered by accretion onto supermassive black holes. The friction and magnetic compression in the infalling plasma converts gravitational energy into radiation with efficiency far exceeding nuclear fusion. A single quasar can outshine an entire galaxy of hundreds of billions of stars by a factor of hundreds or even thousands. The first quasar to be identified as such was 3C273. Detected in 1963 by astronomer Martin Schmidt at Palomar Observatory. Its spectral lines were shifted so far to the red that Schmidt initially could not identify them as belonging to familiar elements. When he realized the shift corresponded to a recession velocity of roughly 16% the speed of light, placing the object at a distance of about 2.4 billion light-years, the energy required to explain its observed brightness became extraordinary. A source that bright, that far away, and varying in luminosity on timescales of days. And therefore physically no larger than the light day across, had to be something genuinely new. 3C273 remains the brightest quasar visible from Earth in optical light. A subclass of quasars, called blazars, are oriented so that one of their relativistic jets points almost directly toward Earth. The jet, moving at close to the speed of light, produces a strong Doppler boost. The radiation is compressed into a smaller frequency range and amplified dramatically. Blazars are among the brightest variable objects in the gamma-ray sky. Their luminosity can change by factors of 10 or more within hours. What makes this change interesting is not just its speed, but what it implies about the size of the emitting region. A source that can vary coherently on hourly timescales must be smaller than a light hour across. The The central engine driving this output, the black hole and its surrounding accretion disk, occupies a volume barely larger than our solar system, yet it radiates more energy than the rest of the galaxy by orders of magnitude. Quasars are also responsible in part for regulating the growth of their host galaxies. When a quasar is active, the radiation and mechanical energy output from the central engine heats and expels gas from the surrounding galaxy. This reduces the supply of material for star formation, effectively quenching the galaxy's growth. The black hole and the galaxy co-evolve. The black hole feeds, grows, and then cuts off its own food supply by clearing the surrounding environment. The tight correlation observed between black hole mass and the properties of the host galaxy's central bulge, the sigma-m relation, reflects this feedback over billions of years. The variability of quasars on timescales from days to years encodes information about the accretion disk physics that no other observational method can access. Changes in the luminosity of a quasar reflect changes in the accretion rate, the rate at which gas spirals into the central black hole. By monitoring quasars over years and decades and measuring how their brightness fluctuates, astronomers can extract the size and temperature structure of the accretion disk, the mass of the central black hole, and the distance to the object through a technique called reverberation mapping. The emission line gas surrounding the accretion disk responds to changes in the ionizing radiation with a time delay proportional to the light travel time from the disk to the gas. Measuring this delay directly yields the size of the emission line region. Combined with the velocity of the gas measured from the width of the emission lines, the mass of the central black hole follows from Kepler's law. Reverberation mapping has been applied to hundreds of active galactic nuclei, providing black hole masses across a wide range of cosmic distances. More than 500,000 quasars are now catalogued. Their distribution across the sky is not random. They cluster. The Klaus Campesano Large Quasar Group, discovered in 1991, contains 34 quasars distributed across a region roughly 630 million light-years in extent. The huge LQG, identified in 2013, spans approximately 1.24 billion light-years in its longest dimension, exceeding the theoretical upper limit for coherent structures that the cosmological principle would allow. Its existence has not been satisfactorily explained. It may require a revision of what we consider uniform distribution at cosmological scales, or a better statistical framework for defining what constitutes a physically coherent structure versus a chance clustering. Quasars are fueled by the same mechanism as the jets from M87, accretion. Gas spiraling into a supermassive black hole forms a disk. The disk heats, the inner edge of the disk, orbiting at significant fractions of the speed of light, generates magnetic fields. Those fields collimate plasma into jets that extend for millions of light-years into the surrounding intergalactic medium. What quasars are not is commonplace in the nearby universe. They belong to an earlier epoch. The supermassive black holes at the centers of modern galaxies, including our own, are quieter now. The gas available for rapid accretion has been depleted. Sagittarius A* today accretes at a rate billions of times lower than what would be needed to produce a quasar-level luminosity. The quasars are glimpses of the past, preserved in the light that left them billions of years ago and is only now reaching our telescopes. That past has layers. The spectra of distant quasars carry encoded within them the record of everything the light passed through on its way to us. When quasar light travels through clouds of intergalactic hydrogen gas, the hydrogen absorbs it at specific wavelengths corresponding to the quantum transitions of hydrogen atoms. most prominently the Lyman alpha transition at 121.6 nanometers in the rest frame of the absorbing gas. Because the universe is expanding, each absorbing cloud at a different distance from us causes absorption at a different observed wavelength, shifted in proportion to its recession velocity. A quasar spectrum displays not just the emission features of the quasar itself, but a forest of absorption lines, one for each cloud of neutral hydrogen along the line of sight. Astronomers call this the Lyman alpha forest. Reading this forest provides a three-dimensional map of the distribution of intergalactic gas across billions of light years of cosmic history. The density and clustering of the absorption lines encode the large-scale structure of the universe, the thermal history of the intergalactic medium, and the degree to which the ultraviolet radiation from early stars and quasars had ionized the hydrogen gas filling the space between galaxies. At redshifts above about 6, corresponding to a look-back time of more than 13 billion years, within the first billion years after the Big Bang, the Lyman alpha forest becomes a nearly continuous trough of absorption, the Gunn-Patterson trough. This tells us that the universe at that epoch still contained substantial amounts of neutral hydrogen, not yet ionized by the radiation from the first stars and galaxies. This period, during which the neutral hydrogen of the cosmic dark ages was progressively ionized by the first luminous objects, is called the epoch of re-ionization. Quasars were among the sources of the ionizing radiation that drove this transformation, but the stars forming in the first galaxies likely contributed comparably or more. Exactly when re-ionization completed, how uniform or patchy it was, and what sources drove it are questions that define the frontier of observational cosmology. The James Webb Space Telescope has begun observing galaxies at redshifts above 10, within the first few 100 million years after the Big Bang, providing the first direct senses of the galaxies that may have reionized the universe. The highest redshift quasars now known sit at redshifts above 7. Their very existence is puzzling. A supermassive black hole of 1 billion solar masses, already in place less than 1 billion years after the Big Bang, required growth rates that challenge models of black hole formation. Either accretion proceeded at sustained rates near the theoretical Eddington limit, the maximum accretion rate at which radiation pressure balances gravity for hundreds of millions of years without interruption, or black hole seeds were already massive when they formed, or some combination of rapid merging and accretion produced the observed giants. The answer is not yet known. But these extreme early quasars, burning at the edge of the observable universe, are some of the most powerful engines of light in cosmic history. Between all these extremes, the singularities, the cosmic walls, the blazing quasars, something quieter and closer to home deserves examination. Something that on a different world might go entirely unnoticed by anyone looking from above, until they look at exactly the right wavelength. Consider now a world covered in forests. Not the green forests of Earth, but forests that might be observed hypothetically from a telescope pointed at a distant planet. The chlorophyll that drives photosynthesis on Earth is not green because green is useful. It is green because the molecular structure of chlorophyll absorbs red and blue-violet light efficiently and reflects the intermediate wavelengths green that it does not use. The energy of a green photon falls in a gap between the absorption peaks of the molecule. This appears to be an evolutionary accident compounded by the specific spectral output of our Sun, which peaks in the yellow-green range. The redundancy of absorption, using 2 absorption peaks on either side of the green band rather than one broad peak centered on it, likely reflects the history of photosynthetic evolution on Earth, not an optimization for the available spectrum. There is a feature of Earth's surface reflectance that astronomers call the vegetation red edge, a sharp increase in reflected light at wavelengths just beyond the visible red in the near-infrared. Chlorophyll strongly absorbs wavelengths up to about 700 nanometers. Beyond 700 nanometers, plant cells become highly reflective. From space or from a distant telescope analyzing the spectrum of reflected sunlight from Earth, this sharp transition from high absorption to high reflectance at 700 nanometers is a distinctive biosignature. It does not occur in bare rock, ocean water, or desert sand. It occurs only in living vegetation. In principle, a sufficiently sensitive instrument could detect the vegetation red edge from the reflected spectrum of Earth as seen from another star system. On a planet orbiting a different star, this signature would be different. The spectrum of light available to photosynthetic organisms would be determined by the temperature and type of the host star. Around an orange K-dwarf star, which emits more near-infrared and less blue light than the Sun, photosynthetic pigments optimizing for infrared absorption might evolve. The equivalent of the red edge, the transition from high absorption to high reflectance, would shift to longer wavelengths. The overall color of vegetation on such a world, to a human eye calibrated for solar light, might appear dark, reddish-brown or orange. Around a cool red dwarf, M-type stars, the most common type in the galaxy, the situation is more complex. Red dwarfs emit little visible light relative to their near-infrared output, and they are prone to intense ultraviolet flares that could sterilize planetary surfaces around them. Photosynthetic organisms on a red dwarf planet would face two contradictory pressures: maximize absorption of the scarce visible light and survive periodic bursts of damaging ultraviolet. One plausible resolution is that complex photosynthetic life, if it exists around dwarfs at all, retreats underwater, where liquid water filters out both the radiation and the meager visible light equally, requiring adaptations for extremely low light photosynthesis. Organisms would evolve pigments capable of harvesting near-infrared light efficiently. The forests of such a world might look to a spectroscope like fields of carbon black absorbing material, nearly opaque across the visible and near-infrared spectrum, maximizing photon capture from the limited supply. Around a hot blue-white A or B star, the problem reverses: too much radiation arrives. Organisms would need to reflect rather than absorb and might evolve pigments that scatter high-energy ultraviolet to protect underlying cellular machinery. The flora of such a world might appear white or silver from a distance, not because there is nothing to absorb, but because absorption must be filtered and rationed to prevent photo damage. These predictions are not purely theoretical extrapolations. They follow from well-understood photochemistry applied to different boundary conditions. The enzymes involved in photosynthesis are ancient and conserved across Earth's biosphere. Because the underlying physics, the quantum-level interaction of a photon with a molecular electron, does not change with location. What changes is which photons are abundant. And the organisms that survive are those whose pigments match the supply. A separate line of evidence supports the view that photosynthesis is not uniquely improbable. Earth itself hosts a range of photosynthetic strategies that collectively argue for the chemical robustness of light harvesting as a biological solution. Deep-sea hydrothermal vents, where no sunlight penetrates, have been found to host communities of green sulfur bacteria capable of using the extremely faint infrared glow emitted by the superheated vent water as their energy source. This geothermal photosynthesis, powered not by a star but by the thermal radiation of the ocean floor, extends the domain within which photosynthesis can occur to environments once considered completely hostile to it. If photosynthesis can function on the glow of a hydrothermal vent, the range of astronomical environments in which it could plausibly arise expands considerably. Purple bacteria and green sulfur bacteria on Earth use bacteria chlorophylls pigments shifted further into the infrared than plant chlorophyll to harvest wavelengths that plant chlorophyll cannot use. They are anoxygenic. They do not split water and do not produce oxygen. Their photosynthesis proceeds through a different electron donor, typically hydrogen sulfide, on a planet where the atmosphere lacks abundant water, or where sulfur compounds are more available than oxygen. Anoxygenic photosynthesis might be the dominant form of light harvesting, producing no atmospheric oxygen biosignature. This complicates the search. An inhabited world might be genuinely photosynthetic, sustaining a biosphere of productive organisms without producing the oxygen that Earth-centric biosignature searches prioritize. Biosignature searches that focus exclusively on oxygen as the marker of photosynthesis might miss inhabited worlds whose metabolisms are chemically distinct from terrestrial oxygenic photosynthesis. On Earth, photosynthesis evolved at least twice independently, in the ancestors of plants and cyanobacteria, which use chlorophyll and produce oxygen, and in certain archaea, which use a different pigment family called bacteriorhodopsins. The existence of multiple independent origins on a single planet suggests that, given a sufficient supply of light and liquid water, some form of light harvesting chemistry is not a rare accident, but a fairly accessible evolutionary endpoint. Whether the telescopes of the next decade will be sensitive enough to detect these spectral biosignatures around a specific rocky planet in a specific habitable zone remains to be determined. The technical requirements are extreme. The signal from a planet's reflected spectrum is typically a part in 10,000 of the star's total light or less. Separating that signal from the overwhelming glare of the host star requires either a space-based coronagraph that blocks the starlight before it enters the telescope, or a formation of spacecraft arranged to cancel the star's light through interference, a technique called nulling interferometry. Both approaches are currently under development or study. The James Webb Space Telescope, launched in December 2021, can analyze the atmospheres of transiting planets by measuring how the star's spectrum changes as the planet passes in front of it. Some biosignature gases, water vapor, carbon dioxide, methane, oxygen, are already within its reach for certain favorable planetary systems. Detecting the vegetation red edge, or its equivalent for alien photosynthesis, would require higher spectral resolution and sensitivity than current instruments provide. But the physical basis for the search is established. If life uses photosynthesis elsewhere, and we have no strong reason to think photosynthesis is uniquely terrestrial, it will leave a spectral fingerprint in the reflected and transmitted light of its world. The most immediately tractable targets are the 7 planets of the TRAPPIST-1 system discovered between 2016 and 2017. TRAPPIST-1 is an ultra-cool red dwarf star, about 40 light-years away, barely larger than Jupiter and about 9 times less massive than our Sun. 3 of its 7 rocky planets, TRAPPIST-1, F and G, orbit within the habitable zone, where liquid water could potentially exist on the surface under certain atmospheric conditions. Their proximity to a dim star means they are tidally locked. One hemisphere perpetually faces the star, while the other faces the cold of space. Whether atmospheric circulation can distribute heat sufficiently to prevent the night side from freezing out entirely is a question that climate models have been investigating, and the answer depends sensitively on the composition and pressure of the atmosphere. The James Webb Space Telescope has already observed TRAPPIST-1b and TRAPPIST-1c, measuring their thermal emission. The data from TRAPPIST-1c, reported in 2023, showed no evidence of a thick carbon dioxide atmosphere, suggesting either a thin atmosphere or a bare rock surface, a result that constrains but does not eliminate the possibility of habitable conditions on the other planets. The habitable zone planets remain observationally challenging because their atmospheres, if present, produce smaller spectral signals than their closer orbiting siblings. Multiple transits and many hours of observation will be required to characterize them. Closer still is Proxima Centauri b, a planet orbiting within the habitable zone of Proxima Centauri, a red dwarf only 4.24 light-years from our Sun, the nearest star beyond the solar system. Proxima Centauri b was detected in 2016 through the radial velocity method, which measures the tiny Doppler shifts in the star spectrum caused by the planet's gravitational pull. Its mass is estimated at approximately 1.17 Earth masses. Whether it has an atmosphere and whether that atmosphere could support liquid water against the stellar flares that Proxima Centauri produces regularly is unknown. A mission architecture called Breakthrough Starshot has proposed sending a swarm of gram-scale light-sail spacecraft to Proxima Centauri at a fraction of the speed of light, arriving within decades, to take images and measure basic atmospheric parameters. The proposal is currently unfunded at the required scale, but it illustrates how seriously the question of nearby potentially habitable planets is taken as a scientific priority. The deeper point is that the search for photosynthetic biosignatures is not a distant aspiration. The candidate planets exist, the spectroscopic tools exist or are being built. The physical theory is developed. What remains is time, measurement sensitivity, and the willingness to look. Everything explored here, the geometry of collapsed stars, the frozen architecture of the cosmic web, the paradoxes of time, the ancient light of quasars, the information content of event horizons, the possibility of dark forests on distant worlds belongs to a single continuous inquiry. It is the attempt to understand what the universe is, how it is structured, and whether the structures we observe are the only ones possible, or simply the ones that happened. The answers we have are partial. General relativity is confirmed at every scale it has been tested, but it fails at the singularity. Quantum mechanics predicts the behavior of particles with extraordinary precision, but it does not include gravity. The large-scale structure of the universe matches the predictions of cosmological models remarkably well. But 27% of the universe's mass, dark matter, remains physically unidentified. Dark energy, which accounts for 68% of the total energy content and is responsible for the accelerating expansion of space, is described by a single parameter in the equations but has no accepted physical explanation. These are not small gaps in an otherwise complete picture, they are large ones. The questions we cannot yet pose are likely more numerous than the ones we can. The instruments being built or planned in the current decade represent a qualitative expansion of what can be asked. The next generation Event Horizon Telescope will add more stations to the existing array and extend observations to higher radio frequencies, sharpening the resolution of black hole images by a factor of several. It aims to produce not just snapshots, but movies, time sequences resolving the plasma dynamics around Sagittarius A star on scales of the gravitational radius, directly imaging the turbulent accretion flow as it evolves. The black hole, rather than being a single blurred image, will become a dynamic object whose behavior can be studied continuously. LISA, the Laser Interferometer Space Antenna, is planned for launch in the mid-2030s. Unlike LIGO, which detects gravitational waves in the frequency range of stellar mass black hole mergers, LISA will be sensitive to much lower frequencies corresponding to the mergers of supermassive black holes, events involving objects millions to billions of times the mass of the Sun. These mergers happen when galaxies collide and their central black holes in spiral together over millions of years. LISA will detect them not as brief chirps lasting fractions of a second, but as signals lasting months to years, allowing continuous monitoring of the in-spiral. Every galaxy collision in the observable universe that results in a black hole merger will, in principle, be detectable. The instrument is essentially a gravitational wave telescope with a field of view covering the entire sky. The Square Kilometre Array, a radio telescope network being built across South Africa and Australia, will conduct surveys of neutral hydrogen across cosmic time through the 21-centimeter emission line, a spectral feature produced by hydrogen atoms in their lowest energy state. Mapping the distribution of hydrogen across billions of years of cosmic history will trace the evolution of the cosmic web, the epoch of reionization, and the growth of structure with a precision that current surveys cannot approach. It will also conduct one of the most sensitive searches for technosignatures, signals produced by technological civilizations ever attempted. The extremely large telescope, under construction on Cerro Armazones in Chile, will have a mirror 39 meters across, dwarfing all existing optical telescopes. Among its primary science goals is the spectroscopic characterization of rocky exoplanet atmospheres, detecting oxygen, methane, water, and potentially the spectral features of photosynthetic pigments in the light reflected from nearby worlds. Whether it will find evidence of life is not guaranteed, but for the first time in history, the question will be answered not by speculation, but by data. And then there is the question of the universe's fate. General relativity combined with the observation that dark energy is driving an accelerating expansion implies that the universe will not end in a big crunch, a reversal of the expansion and eventual recollapse. Instead, it will continue to expand, accelerate. Galaxies beyond the local group will eventually recede faster than light can reach them. Not because anything moves faster than light through space, but because space itself expands. The observable universe will shrink, the cosmic microwave background will redshift to undetectable wavelengths, the last stars will exhaust their nuclear fuel in roughly 100 trillion years. What remains will be called stellar remnants, white dwarfs, neutron stars, black holes, slowly evaporating through quantum processes over timescales so vast. They make the current age of the universe look negligible. Eventually, on timescales of perhaps 10 to the 100 power years, even the black holes will evaporate through Hawking radiation, and all that will remain is a diffuse, featureless sea of photons and leptons in an ever-expanding space-time, approaching maximum entropy. This is the heat death, the endpoint of thermodynamic evolution, the final answer to the arrow of time. The second law of thermodynamics written in the history of the universe leads here, whether there is anything beyond it, whether the vacuum itself eventually transitions to a different state, whether some cyclic cosmology connects this ending to another beginning, the physics does not currently say. The observation continues, the instruments improve. There is a history written in the light of the universe, and reading it requires instruments tuned to every wavelength. The peak of star formation in the universe occurred about 10 billion years ago, the era of cosmic noon when galaxies were forming stars at rates 10 to 20 times higher than today. The Milky Way now forms roughly one solar mass of new stars per year. At cosmic noon, it may have formed 10 to 20. The buildup of stellar mass, the enrichment of the interstellar medium with heavy elements forged in stellar cores and scattered by supernovae, the gradual quieting of star formation as gas was consumed or expelled by feedback from stars and black holes, this is the biography of the universe written in the chemistry of its galaxies. Every heavy element in existence was produced inside a star or in the violent death of one. The carbon in organic molecules, the oxygen you breathe, the calcium in bones, the iron in blood, all of it was synthesized in stellar interiors and ejected into space by stellar winds and supernovae. the gold and platinum produced in neutron star mergers, the uranium forged in the most extreme nucleosynthetic events eventually found their way into the interstellar medium, into the next generation of gas clouds, into the next generation of stars, and into the planetary systems that formed around them. We are, as has been said many times and remains true each time, made of stellar material. The atoms in a human body have each passed through several stellar generations before arriving at their current configuration. What remains to be understood is not merely the inventory of what exists, but the mechanisms that govern transitions, from plasma to neutral gas, from gas to stars, from stars to black holes, from local physics to cosmic structure. Each transition involves processes operating across scales that do not naturally communicate, quantum mechanics governing nuclear reactions inside stellar cores, while the large-scale dynamics of galaxies operate on scales tens of billions of times larger. The bridge between scales is built from observation, simulation, and theory working together. No single approach is sufficient. The universe, patient, indifferent, luminous at every scale we learn to read, dark at scales we have not yet learned to listen to, keeps transmitting.